Hey there, ladies and gentlemen. So I'm going to try to do the last 1/3 of the notes, which is going to cover a couple of topics you're not familiar with, unless somehow you are. I don't know. But it's possible. We'll see. So we've already covered a bunch of this stuff. We covered all of that and all of this and all of this. It's time to move on to the last pieces. We've also covered all of that. It's time to move on to the last pieces from the notes. Now to talk about spectroscopy. And with spectroscopy, we're talking about light, spectrum, where we're shooting light at things. And we're kind of measuring how matter interacts with that light. And so we tend to focus on these three ranges of the electromagnetic spectrum: microwave, infrared, and ultraviolet. And we'll explain why those three. But the big takeaway here is those bold words. If you're dealing with microwave radiation, that causes particles to rotate, as in spin. If you're dealing with infrared radiation, that causes particles to vibrate, as in bounce. And if you're dealing with ultraviolet, that causes electron transition. So I'm going to actually just kind of do that with a molecule here. Again, if you hit this molecule with microwave radiation, it is going to spin, and it's going to spin because it has a positive and negative side. If you hit it with infrared radiation, that's going to cause the bonds to vibrate, woo, 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 woo. Not break, just vibrate, and so I'm just kind of doing like this. It doesn't actually break. And then ultraviolet and visible, that makes electrons actually jump up and down in energy levels, which is why we could see them because they're giving off light. The electrons aren't leaving, okay? They're not quite enough energy to make them leave, but it does make them bounce up and down between energy levels. So spin, vibrate, and transition. Here is a diagram kind of reminding you of the positions of each of these guys. And we'll start off on the low end, radio waves. Radio waves don't really have enough energy to do much to a molecule, so we don't worry about them. That's why we use them in our cell phones and things like that. Rotation, microwaves. Microwaves cause these particles to spin around, which is why when we heat water up, our water molecules are polar and they spin around and cause friction inside a microwave oven. Then infrared. Infrared is our heat, all right? It's when particles vibrate and they rub against each other and they have friction, and that friction translates into heat energy. Speaking of heat energy, I'll scratch there. And it's the bonds between particles that are vibrating. And then the visible and the ultraviolet, the electrons are getting enough energy from the radiation to actually change energy levels back and forth, back and forth, back and forth, back and forth. And then when you get past ultraviolet, there's enough energy to actually break the bonds for X-rays and for gamma rays. Okay. So again, microwaves cause rotation with polar molecules, not with nonpolar molecules, water being the most polar molecule you usually throw in the microwave oven, so it really gets a good rotation. Plus, we like to set the microwave oven at a frequency that corresponds with the frequency at which water rotates, so we can really make the water spin. Infrared, again, so like that double bond or those single bonds, when you hit, particles get hit with infrared, when molecules get hit with infrared, those vibrate up and down and cause friction. And this animation, if it worked, would actually see the vibrating at different frequencies, but it doesn't work. Ooh, this one works. Infrared is a big factor here when we come to CO2. As sunlight hits CO2, because it's got the double bonds, it can do lots of vibrating. You got a lot of interesting vibrating, and those molecules flying in the air can actually hold more energy because they've got the double bonds. So if we have more of those molecules in the air, then more of those molecules can hold more energy. So this is one of the ideas behind why the world is slowly warming up as we have more CO2, is because the double bonds in the CO2 are vibrating, and if there's more double bonds out there, they can hold more energy. When there were less, say if there was only one of those two particles, that energy that's traveling back up from the Earth would just keep going and wouldn't be trapped inside the planet like it is. And so we have almost like this blanket layer that's capturing the energy and helping keep it on the planet. So that's great. And then we have UV. This is your ultraviolet and visible. And these are the colors. And when the light hits these electrons, these molecules with electrons, they actually cause them to change transition levels. And then we see them, and they're very pretty. All right. And then there's different organic, naturally organic pigments that we use to create different colors, and they're all really organic compounds. And now you know each of these little angles and such is actually a carbon. So you can kind of imagine that alizarin, that's carbon, 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 double bond, oxygen, carbon, carbon, hydroxide, and stuff as they all move around. And anywhere there's not enough bonds, there must be a hydrogen hiding in there. And all the different colors you see around you, like the flag behind me, all of those colors are actually artificially made for the most part nowadays because we figured out how to make them. Actually, most of the artificial pigments were first created in Germany. The German chemists were like really good at creating pigments. And if you go historically wise, chemistry really kind of kicks off in the modern day in Germany to a point where up until like World War I, World War II, if you wanted to learn chemistry, you had to learn German first because all the good chemists were German chemists. Photoelectric effect. So if we hit an electron with a photon, sorry, here we have the equation relating the speed of light, frequency, wavelength. C equals lambda nu. The wavelength being lambda, upside down y, nu being the letter that looks like a V, but it's actually a fancy Greek letter called nu. And so as the frequency goes up, the wavelength goes down, and they're an inverse relationship between the two. Now, that equation then gets combined with Planck's equation, E equals h nu, which I know we've seen before, but we didn't use too much. Both of these equations are in your equation sheet, and the constants are in there. So the speed of light's in there. You don't have to have it memorized. It's 2.998 times 10 to the 8th meters per second. Personally, I have put the speed of light in my calculator. So if I push my calculator right there, when I push the letter C, the speed of light is the letter C. And the same thing for the letter H. Letter H is Planck's constant. So I don't type that nonsense in every time. I just go times H or divided by C or whatever because I don't want to have my own fingers make mistakes. So I was very cautious in plugging it in there. Planck's equation, though, and Planck's constant, we need to realize there's kind of a missing unit on the equation sheet. We only deal with the energy of photons. So Planck's constant, 6.626 times 10 to the negative 34th joule seconds, should actually be joule seconds per photon for us because we only deal with photons moving around. But because Planck's constant can be applied to other things, they don't say per photon because outside of chemistry and physics it could be used for this or that. But we're going to just use it per photon. So imagine it said per photon. And that'll make a lot of your concepts in some of these mole equations easier because you'll be like, well, if I have a mole of photons, I have 6.02, 2 times 10 to the 23rd photons because that's a mole. So that's where a lot of kids mess up in here is the Planck's constant really should say per photon. Using Planck's equation, h times nu, and since we were given wavelength, I just rearranged the speed of light equation so it was speed of light divided by wavelength because that would be nu. So I have the speed of light divided by the wavelength and then multiplied it by Planck's constant. That would give me energy, but it would give me energy per photon because Planck's constant is really per photon. And I'm having trouble writing with my mouse, which is stupid because I have a stylus. I should just be writing on the screen. There we go, per photon. So joules per photon. And I need to convert photons into moles, which is what Avogadro's number is doing here, changing it to photons. And it comes out to 27,000, which I need to convert to kilojoules, so 27.8 kilojoules per mole. Kind of the same thing going on in the last one, but just in the reverse direction, and I think you can figure it out and think it through. Um, that funky looking E is the molar absorptivity, which we will talk about in a second. B is the path length, which we'll talk about in a second. And C is the concentration. Finally, something I understand. C is the molarity. Okay, that one is something I have some experience with. Well, let's talk about the other piece. So, if you have a solution and you pass light through the solution, some of the light might get absorbed, shocker, and some of the light might go through. It depends on the wavelength of light. It depends on the solution's color. If the solution is, I don't know, orange, that's going to absorb a lot of different colors, and some's going to get through, some's not. Also, if it's a darker concentration, if it's a higher concentration, it's going to absorb a whole lot more. And so we figured out a way to shine light through solutions and then capture the light on the other side and test how much got through. This is what our lab's going to be about. And depending on the wavelength, we can really adjust the wavelength of light. And it flies through the cuvette, and if it's really concentrated solution, a lot of the light gets blocked and doesn't come through the other side to the detector. So we start off usually by putting a blank in there, and a blank literally is a solution of nothing. It's water without anything in it, and we adjust the dials so that all of the light gets through. So we adjust the dials so at this frequency 100% of the light gets through or nothing is being absorbed. Okay? And then we put our weird solution in there where stuff will be absorbed, and we can measure how much is absorbed. So you have the light source, you have a prism, if you want to call it that, a prism that splits the light apart into the different wavelengths, and then we aim the light through our cuvette, and then we get to see how much light gets absorbed. Now, excuse me, I just recorded a coughing, fantastic. As far as some of those things, one of the things in there is the path length. I think it's the letter B. Is B path length? Yeah. The path length is literally how wide is the cuvette. So how long is the light traveling through the solution? How literally, what length is it traveling through that? Because if the cuvette was extra wide, then more and more of the light would get trapped as it hit the solution. If the cuvette's really skinny, it's going to get through the solution quickly. So the width of the cuvette impacts it also. Oh, meh, meh, meh. As you adjust the wavelength, you get different amounts of light through. So what we'll do is we set the wavelength at we set the spectrometer a certain wavelength and see how much light went through. Then we change it to a different wavelength, see how much light went through. And so this is a graph, and you're going to actually do this in your lab. You're going to make a graph at different wavelengths, how much light got through. Here's the equation. Again, the path length is actually how wide is the cuvette. The concentration is the concentration, the molarity of it. And then the molar absorptivity constant is a constant that tells you how much light is being absorbed at that wavelength. And so we're going to get some data from our lab, and we're going to graph the data. We're going to compare how much was absorbed versus the molarity of the solution, and then we'll make a graph. And then I'm going to give you an unknown, and you're going to figure out, okay, well, if such and such was absorbed, boop, boop, that's the concentration of the unknown. We got you, Mr. Murphy. Okay? You could also vary the path length, right? You could keep the molarity the same and change the path length also. Also, get the hiccups. So you're going to create a graph, and then you're going to have an unknown that you're going to try to figure out. And there you go. It's pretty simple. And all of these, I'm just going to fly through these because they're just ratios, and you plug numbers in and you solve, and you guys wouldn't have any trouble with that. Okay. So, in summary, spectroscopy is shining light through things and seeing how it interacts. Does it cause vibrations? Does it cause rotations? Does it cause electrons to fly off? And does some of the light get absorbed? So as our light is flying through the spectrometer, hitting those particles and getting absorbed, it's probably making some energy transitions occur, right? Some of those particles are going up and down and being released. Some are being turned into heat energy, all sorts of fancy things. And this is called Beer's Law. It's kind of difficult to Google Beer's Law with a LCPS account because You're typing and searching for beer, and suddenly you're like getting blocked for doing something totally legal.